control the hardware, on a very low level, such that I can build my own quantum computer at my house.
With your 3D printer. And
yes, exactly.
Pass that between you as you speak.
I think in the very, very long term, yes. But for the moment, certainly not. There's just too many people are looking to try to figure out what the secret recipe is. It provides a competitive advantage. There's a lot of tension because most of the people who work in this area are historically researchers and academics. They all know one another. They all go to the same conferences. They frequently went to the same schools. But most of them are working for paymasters that really would like to keep as much under the table as possible until it's clear. I mean, they always ask to publish, and we publish as much as we can. We like to be open, but some stuff gets sort of. I would for a metaphor, consider the whole risk V movement. So we finally have, after 50 years of computers, an open source computer design. And even that's not a computer design, that's just the instruction set. Okay, so it will happen, but it will take a generation or two, in my opinion.
Well, I'll take like a contrary, if you want to go down.
Please. No, we want an argument. I know part dipping.
Yeah. So obviously in a lot of, do I have to use this?
Well, for the is this being diffused, broadcast?
Is anyone telling me I'm in charge?
You want to use the mic.
Yeah, great. So I agree with Kevin in terms of where some of the industrial players are going, but a lot of the advancements in this field are still happening in industry, and there's actually a lot of open source software that goes all the way down, even available today. So there's something called Q-codes, which is used for controlling superconducting qubits, and there's a bunch of groups. It's actually with someone here who works on that project. Maybe they're not here now. There's open source controls for DACs and ADCs, depending on your platform. There's Arctic, which is an open source project for fast feedback on ion traps, which is another kind of quantum computing. And these things go this is all the way down to the metal. So I think there's going to be a proprietary stream, and that might be the leading stream, but there's already sort of open source bases in academia, and I don't think those are going to die out. At least I hope that they're not.
Does anybody from the audience has an opinion on this? Anybody works on their own?
So one thing I was wondering, because isn't that lack of access to the control, like software and hardware, is it actually prohibitive for making open software in this regard? So the fact that I personally cannot access, controlling, ion trap, doesn't it make, impossible for me to access this? So it might be open source, but still only for a couple of groups that actually have access to hardware. So in the next, as Kevin said, in the next generation, it will be prohibited to some expansion of these projects.
And to some, just to follow your point, to some degree, the firmware is only relevant to a very particular implementation. I mean, and that's sort of the point. I mean, what we're trying to get, Circ down to the lowest level that is useful to people, working on machines in the abstract. Yeah, we got firmware, but our firmware is different on for every chip, and modifications to the chip will mean modifications to firmware. So open sourcing that firmware until we actually start having standard. Well, again, Linux became possible because there were PCs. Okay, so once there is a ubiquitous, cheap quantum platform, then I think the open sourcing of the low-level software will make sense.
Just that, yeah, I think that while each piece of hardware is bespoke and relatively bespoke to the companies, I just fundamentally agreeing with that point, that the very second I think that you get some model where you could reasonably expect a large number of people to use it, or maybe just even as we start to scale up and you start to see common components appear between the different refrigerators, say, that are more accessible, then you might see more standardization of the software. But until that point, I don't think so, other than maybe in very narrow verticals where some things are useful and some open source components are used deep in the stack.
I would love to hear Josh's
Yeah.
because John has this barrier. I have to have a bridge and all to it, right?
Yeah, that's what I was going to say. So in quantum photonics, we're using, for a lot of our equipment, off-the-rack stuff that a lot of universities and other scientific labs use. So there is a lower barrier to entry. The thing is, it will still take time because we're still standardizing exactly what our architecture will look like on the quantum photonic chips. So I guess And in the very short term, we'll be doing optimization based on user submitted jobs and how can we optimize and make this process more efficient. But in the long term, definitely I see a process for once we've standardized the quantum photonics. The one thing that would be a barrier though are the detectors, so the measurements at the end of the circuit. So at the moment we're using two very high quality, best in the field, photon number resolution detectors, PNRs, from NIST. And these don't require supercooling, but they require a degree of cooling. So these aren't as accessible as the rest of the photonic setup we have. So that's still a bit of a barrier.
Right?
Yeah.
They're 4K.
Yeah.
So based on your thoughts, do you think it's a good move to try to make a DIY quantum computer, or maybe from the photonic approach, what's the minimum funding to build some prototype, not a quantum computer?
So actually that's very possible. You can build a quantum photonics chip with off-the-rack stuff. It won't necessarily be universal, and you won't have access to all the quantum algorithms. The very basic thing, you could build a chip that does something with the classical properties of light and then introduce some quantum properties that way. So there are easier ways to access it, definitely in quantum photonics. And I think that's the approach we'll be taking. So we'll have an iterative procedure to our devices as well.
I think one point that is worth highlighting is like the number of startups you're seeing in the field kind of shows that it is possible to sort of, in some sense, build a quantum computer in a hobby sense. I mean, these are obviously, I have no idea what the barrier of funding is for these places because I'm not involved with that side of the building, but you do see that you're getting more and more of companies and research groups at universities and various people getting involved with this field, which still, again, I mean, there's a decent amount of infrastructure goes into that, but it does show that it's not so high that you need, giant companies to do the funding right from the beginning. Sure.
Just to say, the real cost, the real obstacle isn't cost, it's expertise.
I agree with that.
It's a question for Google. Do you only take interest in superconducting qubit, or do you have other technology, or will you be interested in other technology, or will you drive interest in other technology?
Well, the core team that is building the hardware have invested many years in trying to master the superconducting technology, and so we don't have hardware teams working on anything else at this point. The algorithms guys, on the other hand, I mean, the beauty of quantum information theory is that it doesn't matter what the qubit is composed on, the behavior is the same. And so the algorithms, should be applicable wherever else. And I sometimes joke that if somebody else actually comes up with a better scheme, I'll be a faster, cheaper, more stable, hardware substrate. I'll be the first to say, let's move to that. But I try not to say that in front of John Martinez's team because it would break their hearts.
That's really the lesson is that if you don't have patents to defend yourself, you're going to be in trouble. But of course, that costs a lot of money, and for most startups, that's not an option. So my question basically to everybody in the community is how do we mitigate against that? And I think Google obviously has a very good record on patents for open source.
I do want to get the others involved, but I'll point out that I mean, I've worked for IP companies that that used patents as a weapon. Google tends to try to use them as a shield. There are things that I've invented, not in the quantum field at Google, that we didn't patent, but we filed the paperwork to prove that I'd invented it so that nobody else could, because we didn't want to shut it off from the world. I mean, Google does that kind of stuff. Now, are we going to do that with key quantum discoveries? I do not know. But again, historically, we're fairly open, but you raise an excellent point.
it's a good point. There are some things that other industries have done and some other things that we could, as a community, think about doing. So there's examples of, one thing you can do is have like a defensive patent consortium where where groups of startups will pool IP. So maybe they each have a few patents, but if they pool their IP for defense, then then they have access to it if any one of them gets sued by a large company. And there's other kinds of consortium models and stuff like that. I'm not going to go too far and advocate for any particular one for our field. But it's a thing to think about. And there are some of these groups that are starting to come together, like the Quantum Open Source Foundation would be a group that could think about this. There's something called the Quantum Economic Development Consortium in the US that has most of the big companies and a lot of startups in it as well. Google's in it too. So there's some space for us to think about how to do that in our industry, and we can actually act on it. It's not something we just have to talk about. So that's good.
I guess the only other point I would add to that is like there is definitely different types of patents that companies focus on. So for instance, D-Wave, we're a lot slower to patent or to otherwise IP protect like algorithms because we want more people in the field and we want more people in the ecosystem. So, there's incentives, the same incentives that had us open source our software in the first place is the incentives that keep some of that stuff unprotected or otherwise just defensively patented. But as you get sort of, maybe harkening back to the first question, as you get sort of further down the stack, the incentives start to switch a little bit. So,
My question is regarding more from a single web developer, So I'm a single developer and I wrote the awesome quantum machine learning in 2016. It's reached almost 1,000 stars. And then later I dropped completely in 2018 because it's very difficult to reach a simple developer to start developing in this platform. Because it took around 1 year for me to learn the basics, and I prepared almost all your Google, IGM, and all the external other products as well, and some articles as well, and as well papers, theory papers. So I kickstart for all the new quantum machine learning algorithms as well. But the main problem what I face is if I'm teaching someone, having basic knowledge of coding capability, he can't continue. The next step, nothing. He can't do anything. And only it's useful for a researcher or mostly people who is well know about the more theory stuffs. So what's your opinion, point of view, how it can be reachable to a simple developer so that it's useful for everyone to contribute? Because my contribution totally wasted, went to waste actually 1 year. But still people are using. But anyway, it's no. If I want to make a new open source product or something, that I planned, but I dropped completely. So what's your point of view on this one?
I tend to agree with you. I think we sometimes make, especially the physics, very hard to access and not very accessible to people who want to get involved and want to get engaged. So I think we definitely have to do a better job at doing that. I agree with you 100%. There have been times where I've had to learn the other frameworks from the other companies. So especially when I was doing the Penny Lane Forest plugin, I think I started with PyQuil version 1.9 and halfway through PyQuil version 2 came out where there were there were lots of API breakage. And it happened really fast, or I didn't really notice, but I pip installed upgrade and everything broke. So even from a quantum researcher, it's difficult to keep up. And so I think it's something we definitely need to improve on.
What's your date, improvement day? You are planning something or to create some frameworks or easy to understand format or something?
yeah, so at least from D-Wave's perspective, we started our open source project a little bit later than I think some of the other folks up here, but it went live maybe about a year ago. And the whole purpose of that was, number one, to sort of bring it higher level and higher level and higher level so that we could access groups. And I think like all of the projects that are going on from all these different companies and groups are starting to reach a level of maturity that you're not going to version 3.0 and then 4.0 every week. You're at least have months in between these things, and that gives you just enough stability that you can reasonably start reaching up higher in the API. And then I think the other point is that part of the reason that at least for us, that we went into the open source space is because we want just more people in the ecosystem asking more questions, making more connections, because then my best case scenario is someday someone's going to ask a question on Stack Overflow and someone else will answer it without us ever having to have been involved, right?
Achievement unlocked.
Yeah, exactly, yeah.
Stack Overflow works.
Yeah. So I think that just getting more people in the ecosystem creates that connective tissue that then lets the next people who come in have a little bit of a softer landing. And you can sort of build up from there.
Another thing to remember is that a lot of these packages, a lot of them are really about quantum gates and quantum computing, but a lot of them have the classical software in them. There are web frameworks in them. There are APIs in them. And all of these things also need to work really well and could be made better. So as a web developer, I think there's a lot of ways that you could contribute, because a lot of people who are developing the physics code are good at the physics, but not at the web development. And this would be actually a very, very useful way to contribute.
There's a fellow in the back who's been raising his hand several times. But no, okay, whatever. Yeah. Because you're directly in my line of sight, I see it going up.
Go for it. Okay. It's kind of not exactly the same, but when I started working on the quantum computation stuff, it happened to be very clear that everyone is using Python for that. Why? I could really think about a lot of better programming languages. I mean, even if I say Lisp.
Yeah, that's a good question. If you come to tomorrow, I think there's some other ones that people talk about. So come check out those talks. There's a plug for those. I can tell you about why we ended up with Python at Rigetti. There's some Lisp, but why that was the interface we chose. It was based on the target audience that we thought would be using this. So it's typically people who are a little bit more mathematical programmers, maybe a little bit more scientific programming. They know vectors, so that's ML people. And Python is kind of the lingua franca for that initial group. And it has a lot of other reasons that it's sort of easy to prototype in. So that's why we ended up with Python on the front end. But there's tons of reasons why in the long term, it's almost certainly not going to be Python.
I'm not so sure, because there's so many frameworks are growing by the day. I mean, they're getting so complicated. Do a refactoring on that within the different programming language. It's next to impossible. It's not going to happen. I don't see how that could happen. You have to start anew. You'd be a new startup.
We might have real quantum programming languages at some point.
Yeah.
Like all of these are kind of like embedded. Q# from Microsoft is one to check out. That's kind of actually, but that's already got a lot of barriers to entry. It's kind of like maybe the hardest way to do it. It's multi-paradigm already. It's like based on F#. So I think there's at some point room for proper quantum programming languages.
I think another reason that Python is attractive is that, it has some of these tools coming in like Cython, and it has pretty good C++ bindings in the first place. So I think most of the stacks here are all sort of Python interfaces, but have some C core for at least some part of it. So when you're doing these sorts of things, you want to both address the first point, which is make it easy to access, but then you want to also give it performance. And so at least for us, that cost benefit analysis has resulted in writing it in Python, prototyping it in Python, having it live out there for a little while, and then start knocking down the tall poles by converting the intensive parts into C. And so when you actually look at the total execution time of sort of an average job, I think, again, on a lot of these stacks, what you'll see is that it actually spends a lot more time in C code than in Python.
And can I just add to that one other reason we went with Python, there's two smaller reasons in that because we're working with the hardware team is also kind of prototyping a bit as well. So Python's a good language for prototyping. And on top of that, we found that Python's just really easy to install. So we have more complicated packages where we have C extensions, we have C++ extensions, and we have Fortran extensions. And with Python, we can have a pipeline where we build the binaries for all the operating systems and Python versions we want to target. And for the user, all they have to do is pip install, and they don't even have to worry about dependencies.
Also, Python has one of the lowest barriers to entry from like a completely person like out of programming. If you're not an expert, you can learn Python probably the most easy.
Yeah, in Google's case, we had a certain amount of experience with programmatic interfaces to the various REST APIs for the cloud services. And in many cases, we started out publishing it in Java. And what we found is, everybody's saying, okay, Java's really nice, but couldn't you give us something that's like, Python? And so, so that was already sort of a trend. We knew that the users of cloud compute in general seem to like to use it for the aforementioned reasons. It's easy to use, you get quick feedback, it's not this very long compile debug cycle. And then, very significantly, of course, we did TensorFlow. And yes, there are TensorFlow bindings for other languages, but nobody ever talks about them, right? It's all being done in Python because of that dominance in the data science space. And keep in mind that the official name for the Google Quantum team is the Google Quantum AI Lab. So there's that influence that comes in.
Just one point. I
to address actually to your question, so I almost started 2008, the machine learning platform. So that time everything is MATLAB. So we'll put everything in MATLAB. That's a good one. And then it's a competition in the world. And to be frank, then some people started writing Python in Python the libraries, and then it's emerged. In 2012, I don't have that much keep actually. I mean, it will grow in a very high state. In 2015, TensorFlow, then that's maybe.
Okay, so maybe two.
I just might add this. We're thinking that performance benefits from switching from Python to C or C++ will save you computationally. Well, that's not quantum computing, right? We're here for the exponential speed up runs. And once you get there, the actually the choice of language and you are maybe talking to make it to there, but it's not exponential speed up. And then in that case, prototyping and fast development, I guess, are more important than
I just had my experience when I worked with Qiskit is just, it was a huge mess to understand what happens. And there was, the prime reason for that is that you don't have types nowhere. You have to debug through the code to understand what it is. And it's like, as I am a software engineer actually, and for me it's like, that's code hell. You know?
I would say as well what you are used to.
Yeah.
If you use the types, then you will miss them. If you don't use them, you can survive Python and so.
Actually, on that. So on that types point is a really good one. Languages is always a fun topic, right? Everyone wants to talk about languages. So in quantum computing, debugging is tough because if you have n qubits and you want to print the state, you're going to end up with 2 to the n complex numbers. So if you have 100 qubits, you no print statements. So your debug flow is a little weird. And so that makes me think that in the longer term, we're going to need languages which have sort of more formal, they have actual type systems so that we can use this as a way to control formally what we're doing when we can't do normal print debug flows. So that's another reason to think that we'll move a little bit.
And it's worse than that, because you can't do a breakpoint restart.
Right, yes. Yeah, so debugging is a big thing.
Speaking about debugging, we actually have a project tomorrow which is inspiring to be a quantum debugger, visual debugger. So I invite you to check it out tomorrow. Debug. But speaking about like productivity and being able to like write code and debug it, like last year we spent a lot of time like working on different research with Mark in our company, and basically what we quickly figured out is that we developed some code for we get this platform, we developed some code for DOS platform, and if you wanted to try IBM's platform, Qiskit, we would have to like port all this code tailored for Forest to IBM Qiskit. And if we wanted to compile it all too. And if we wanted to like try Circ, it will be the same thing. So do you guys think that, and Mark is going to speak about it a little bit in his closing remarks, but I would be interested in knowing like, what do you guys think about standardization or like pulling these projects together, like Project Q is doing or ACC is trying. Any thoughts about that?
So I definitely that ease of use is good. Most people who program on multiple platforms. So making it easier to do that is important. There are things that are the way to make that easier that I think is a good one is this transpilation stuff. So there's like a chasm to quill converter, and these kind of and the reason I think that's better rather than standardizing is it's a little early to think about this field standardizing. We still need to come up with a lot of creative different ideas. We aren't at a stage where people are running quantum computations and they're much faster, they're much better, and we know what the patterns are, and we know how to do quantum programming. Like, we don't know how to do any of these things. So having a more diversity in approaches is, I think, important. And so I'd actually be careful about early standardization, but translation, definitely. I think.
Just to respond to that point, I mean, this comes up at just about every conference, and and I will echo the point that it's a bit early to think about standardization, but you can think of standardization sort of as a horizontal and a vertical axis here, in as much as do we actually want to have a common low-level language? Maybe at some point. Do we want to have a standard high-level language? Yeah, maybe at some point. But ultimately, again, we're talking open source here. So ultimately, what's going to happen is that there are going to be, library APIs that are relatively high level that do things that are useful for people that are going to get where the implementations underneath may be actually device specific, and you link in a very large sense of the term with the one that's required. I think that's the sort of thing that will evolve. But it's early days. We don't know what's most efficient.
Can I just add on that when we were developing Penny Lane, we had the idea as a QML framework. But what we noticed after developing and having people use it was that sometimes you would use it even though you didn't want to access any of the gradients or the QML features. And sometimes even when I have a Strawberry Fields program, I'll just do it in Penny Lane because it's faster. And it allows me to quickly swap it out and try QIS case or something. It's not a proper high-level abstract replacement because you still can't control any of the lower-level hardware optimizations. You're still constrained into this QNode encapsulation where you have to work with expectation values. But playing around with that has got me excited for the future where eventually there will be this higher-level library that allows you to mix and match and change devices.
I think because the D-Wave architecture is so different than a lot of the other architectures here, it's sort of hard for us to talk about standardization in the same way, but maybe I'll put a slightly different slant on it, which is like one plug for standardization I like to see is standardization of benchmarks. Because right now it's very much the Wild West for different companies doing different benchmarks, and I think that can be both a good thing and a bad thing for everybody, but having some more standard targets that then can be compared would, I think, really help the field.
Yeah, what's the quantum MNIST? Right, like that's done. These kind of standard tests have done a ton for machine learning.
So my question is pretty naive. I want to know like what kind of benefits this quantum computing can bring to a common man walking on a street or is there some kind of problems which you as a quantum computer scientist see in future that you can solve for some common man, or is it only for
I guess maybe I'll take the really easy answer, which is like in the same way, I mean, in a analogous way to the way that like machine learning has sort of touched on everyone's lives in the sense that it was like sort of it's a refactor of a bunch of other old concepts that suddenly if you put them in the right way and sort of put the right hardware behind them, you can get a lot of benefit from that. I think sort of the dream of quantum is to have sort of a similar effect where it's like it in some way touches very lightly on everybody's lives, but probably at least in no time that I'm imagining are you going to have it on your wrist because just the way the hardware is designed. So I see it as being potentially in the future like everywhere, but also kind of at a level or two abstracted away from the average use case. But I'd love to hear actually other people's opinions. Josh.
I agree 100% with what you said.
Well, again, when you say benefiting, the man in the street, okay, and I don't take you to be asking, is the man in the street going to be carrying around a quantum cell phone, okay? I mean, again, give us enough centuries and people will, of course, have something like that. But no, in the near term where I think it's going to have an impact, and again, I did not talk very much about the applications. I was really much more interested in explaining how the system works and how that influences the design of the language that we open sourced. But if you look at applications that are seriously being investigated now, is for example, with quantum superposition, you can do a much better job of global optimization of, for example, traffic management for public transit or for taxis. If you use Waze, Waze will tell you where the traffic is, but Waze creates its own traffic jams because it directs everybody to what is at a given moment the optimal path. What you actually need to do is you need to distribute the traffic in some intelligent way where you're not creating new traffic jams. And that's a hard problem. And there are quantum algorithms that will tend to get there. And so people like Volkswagen are investing in looking at it for things like that. That's just one example. There are others.
I mean, I'll put in one other plug. So there's sometimes people talk about a big application space for quantum computers being the quantum simulation, which sounds like it's very esoteric. But what it actually means is designing molecules with computers. So we design planes on computers now, not in wind tunnels, and that's why we've been able to go from the Wright brothers to jets so fast. But the molecular equivalent is still throw a bunch of PhDs at it. If you know anyone who did a PhD in chemistry, they might have spent their entire PhD figuring out how to make a couple molecules. But in the long run, if we can use computers to help design molecules, then the man on the street may have organic batteries, solar cells that are much more efficient, impacts on making fertilizer cheaper. The stuff that we design with quantum computers, I think is going to be a very, very impactful in the long run.
Yeah, I know something I wanted to add to this that I don't know, I'm not sure that I feel like to be discussing is that it's already impacting it if you think about classical algorithms that are inspired by the quantum framework. So like some recent work, for example, on machine learning algorithms that Ewan Tang, who is a young researcher, came up with will not be possible without thinking in a quantum way. So even if we will never build a quantum computer,
Ewan Tang's work.
sorry,
Ewan
Ewan Tang's work, yeah. So even if we will never build a physical quantum computer, it's already impacting classical computation. So it's already the 111 risk because we use machine learning algorithms. Ewan Tang's already without compared to the classical ones. So they are already impacting it.
That's a great point. And there's more even beyond Ewan Tang's work. There's actually several kind of other examples. There's a contrastive divergence algorithm. Yeah, the new recent one. Yeah, it's a really good point.
It's actually like good applications. What my page mentioned is fingerprint. So for basically in current programming fingerprint application, fingerprint recognition is if your fingerprints are any damage in your fingerprints, it's very difficult. In any of the system in the world, it's not doing full recognition of all the fingerprints matching. If it's doing a single comparison, it's only the database. There is no mechanism to refer n number of database and see fingerprint is matching with this one. It's very difficult. So in that scenario, this is one article says, and this is a very good application for quantum computing and machine learning platform. Then is a DNA, so it's already mentioned.
All right, so maybe the last topic I wanted to discuss a little bit selfishly was this idea of having some kind of open source foundation for quantum computing. What it should do, and really, like, the reason we started it was after the realization we worked on this review paper for quantum computing software, and we evaluated multiple frameworks, multiple projects, and most of the big projects did pretty well, but there was, smaller projects sometimes completely forgo documentation, or they don't have any tests, and we kind of thought that we should, in the long term, promote these like good practices and promote open source, promote the good software engineering way of doing things. But maybe there are other things like things that Will mentioned that we should be doing, or we should be thinking about doing. And I'm curious, like, what they might be. So happy to hear about that.
I mean, just to echo something I said earlier, like I think just having a community that we can grow, getting more people in the ecosystem on all of the platforms, some of the platforms, comparing the platforms, using, doing web development, doing, anything really, just getting more smart people doing more things on all these systems, I think would help all of us, because then that creates that sort of competition and ideas and generating and just all the energy that we need to do the amount of work. Because, one of the things about working at one of these companies that I think is most fun is like, there's so many ideas, there's so much low-hanging fruit, and there's so many things to try that, we could have 10 times as many employees and we wouldn't be able to try it just on the software side, right? So having more smart people in the ecosystem trying those things can only really be a benefit to the field as a whole.
Yeah, I agree, and I also think it's really useful and really important to have a sort of central area that people can refer to and see all these different quantum software projects. There are awesome lists on Facebook, but this is one of the first places that, instead of just listing it, also discussed the different projects and said, these ones have been, they're not active anymore, these ones are still active, these ones have decent documentation. I think that's a very important thing, so we can get an overview of the quantum software ecosystem, especially for users who are new to it or don't have a quantum background, because a lot of the documentation that already exists was written by physicists, and it's something we can improve upon, and something like the QOSF can definitely help with that.
Yeah, I particularly agree with that last point. There are things to be done. I don't think it's critical yet simply because the size of the community, the number of people who are actually doing development is relatively small. It would be a total exaggeration to say that they all still know each other, but it's a pretty small group. And as the more things scale, the more the signal-to-noise ratio degrades, and the more points of coordination, clarification, documentation, standardization become important.
So there's all the fully connected graph, but it's fairly densely connected still.
I have like an observation because I work at the Ford Technology, and we're running this program for people who like to learn quantum computing and do some projects, but they like don't have an idea by themselves. And actually, after like talking to many people, like I see this pattern that there are a lot of people who are very motivated to actually learn quantum computing and do some stuff with that. Then they start to like learn and dig deeper and try to understand very well how these qubits actually work and interact. And in the end, well, they might get some understanding, but some of them get discouraged because they just can't, like, you know, understand it deeply. And on the other hand, there is this other approach that I personally like, of treating some of these algorithms, like, I don't know, QA way, like a black box, and trying to like poke it here and there and see what happens, and then in the meantime, like, you know, getting a better feel of how it works, reading paper, checking it out, and you know, like joining this like theory and practice, and starting from like a higher point. And like I personally think it has like it's easier this way for many people who are not theoretical physicists or experimental as well. And so my question is, do you have any thoughts about it, and how to actually like, do you think like promoting this high-level approach is a good thing, and how to actually explain to people that you don't need to understand all the nitty-gritty details of how the quantum computer works to do a meaningful job, to do a meaningful research, just by like checking some hypotheses and like pointing direction for other people.
Yeah. I think that's a great point. Most of us don't understand these machines all the way down to the physics of the transistors, right? And it's kind of contrasting maybe like a bottom-up approach, which is what people learn in physics, of like, here's the linear algebra, as opposed to a problem-first approach. I think this might be something that the Open Source Foundation could help with. They could have a list of, you know, problems of like, here's a way to get started, or like little challenges. OpenAI puts out requests for research challenges. There could be smaller ones that are a little bit educational, of like, you know, start trying to implement this, trying to solve this problem. I think that would be a good thing to have.
Let's thank our panel. They have been
Yeah, I think taking the